what the manufacturer's design criteria are, and also how contractors size these things so that if one is installed properly, then it'll work and give the indications temperature-wise and so on that you would expect. So in order to do this, our program consists of a videotape which explains heat pump operation. We also have a trainer which will show you the various cycles, and it gives you more time to see what you could expect during the various phases of operation. And then I'll get into the sizing and to the manufacturer's design criteria, and some tips on what you should look for to determine proper operation. And then Trish will tell you what TEP does on their inspections, how to use the meter, and then we'll close the meeting with a question and answer period to find out what you're running into and what your questions might actually be. So at this time, I'd like to go ahead and start running the tape, and after that, we'll continue with the presentation. Don't know how to do it. Is anybody?
Power. No. Who's on?
What?
TV's on. Okay. TV's on. No, it was on. Yeah, there it is.
You guys see what
We need to move the podium. Yeah.
You see?
At first glance, it seems impossible to heat the glass of water by using the ice cubes. Moving heat from ice to water violates a fundamental rule used every day in heating and cooling equipment. That rule says heat always moves from warmer to cooler things. Moving heat the other direction is not easy, unless we use a heat pump to do it. Extracting heat from cooler things, namely the cold outside air of winter, and moving it to warmer things, the inside of our homes, is the job done by a heat pump, and it does it very efficiently. The heat pump violates no laws of physics. Heat still always moves from warmer objects to cooler objects. Surprisingly, the thing the heat pump uses to move the heat is refrigerant that, in summer, is used by an air conditioner to take heat out of the air inside our homes and move it outside. In winter, the heat pump uses the refrigerant to move heat in the opposite direction. Heat is taken from outside to heat the inside of the home. The heat pump does it by reversing the work of the air conditioner's indoor and outdoor coils. In its simplest form, the heat pump is a reverse cycle air conditioner with some very important components added. An air conditioner cools by boiling refrigerant under low pressure. The heat necessary for the boiling comes from the warm air passing over the indoor evaporator. The refrigerant then gives up the heat to the outdoor air at the condenser. The inside of the home is cooled, and in a sense, the outside of the home is warmed. Reverse the two coils, and the inside of the home is heated, using heat taken from the air outside the home. Even if that air is well below freezing, no matter how cold the outside air gets, it still contains some heat. The heat pump's job is to extract as much of this heat as it can and discharge it to the inside of the home. A heat pump uses the same principles as an air conditioner, except the evaporator is in a temperature that is already cold. The condenser, on the other hand, is indoors, where the ambient is at a lower than normal condensing temperature. A heat pump operating with the indoor coil as a condenser typically has a condensing pressure of about 210 pounds per square inch. For R22, this is a coil temperature of about 105 degrees Fahrenheit. Return air temperature is normally between 65 and 75 degrees. Outside the home, for an ambient temperature of 40 degrees, the evaporator operates at about 44 pounds per square inch. With 40-degree air moving over the condenser, coil temperature is about 21 degrees. The temperature difference across the outdoor coil is about 19 degrees. Under these operating conditions, the outdoor coil absorbs approximately 70 BTUs of heat for every pound of refrigerant that passes through it. Even though the outdoor air temperature is at 40 degrees, it contains more than enough heat to support boiling of the refrigerant. For a 3-ton heat pump, the refrigerant flow rate is about 520 pounds per hour. The heat extracted at the outdoor coil every hour is approximately the 36,000 BTUs needed to heat the home. The heat pump has accomplished its impossible job, moving heat from a cooler location to one that is warmer. And it will do it with an efficiency that also appears impossible. In a high-efficiency design, a 3-ton heat pump uses about 4 kilowatts of electricity to move 36,000 BTUs of heat. 4 kilowatts is equivalent to about 13,000 BTUs. That means for every 1 BTU of electrical energy showing up on the electric bill, the homeowner gets almost 3 BTUs of heat. The value of the heat pump is quickly seen. This ratio of heat energy output to electrical energy input is called the coefficient of performance, often referred to as the COP of the heat pump. COPs above 3 are available in higher efficiency heat pumps. Straight electric heating furnaces, on the other hand, always have a COP of 1. For 1 kilowatt of electricity in, there is 1 kilowatt of heat energy out. This high improvement in energy use is a major reason for the success of heat pumps in many applications. Reversing the job of the 2 coils in an air conditioner to convert it to a heat pump is not a simple task. At one point in the early history of the heat pump, the reversing of the coils was done by physically moving the 2 coils. Needless to say, this approach did not last very long. The universal method used today to reverse the job of the 2 coils is to use a 4-way solenoid valve, or as it is more commonly known, a reversing valve. Reversing valves control the function of the indoor and the outdoor coil by redirecting the flow of the compressor piping. All reversing valves have an inlet from the discharge of the compressor and a suction connection to the compressor. 2 additional tubes connect to the indoor and the outdoor coils. The reversing valve does its repiping job using an internal slide which can move to one of 2 positions to direct compressor flow. The slide can move to the heating position where the indoor coil is connected to the discharge of the compressor. This makes the indoor coil the condensing coil. The outdoor coil is connected to the suction side of the compressor, making it the evaporator. In cooling, the slide is moved to the opposite end of the valve body. The indoor coil is connected to the suction side of the compressor. The outdoor coil is connected to the discharge of the compressor. Evaporator and condenser are connected for cooling. The force to move the slide comes from the pressure difference of the high and low side of the heat pump itself. The control of system pressures to move the slide is done by a pilot valve mounted to the valve body. The pilot valve is electrically operated by a 24-volt coil connected to the heat pump control circuit. Both coils in a heat pump have the capability of being either a condenser or an evaporator. Metering of refrigerant is a little more complicated than in a straight air conditioning circuit. One thing is certain about refrigerant metering in a heat pump. Each coil must have a metering device for use when that coil is operated as an evaporator. In many heat pump designs, this means 2 separate expansion valves. Only one of the valves is used at a time, however, so a check valve must be used to route the refrigerant around the other valve. Metering can be done with a combination of an expansion valve on the outdoor coil for heating and a fixed restrictor on the indoor coil for cooling. Again, a check valve is used to control flow. Fixed restriction for metering to both coils is common in some designs, but it must be done in 2 stages. The first stage is a fixed restrictor. The second stage is also a fixed restrictor with a check valve across it. The heating cycle requires more restriction than does the cooling cycle, so the check valve forces flow through both restrictors. The liquid line restriction then is the total of both restrictors. In cooling, one restrictor is bypassed by the check valve, leaving only the other restrictor for metering. Refrigerant metering, while more complex than a heat pump, is normally very reliable and contributes much to efficient evaporator performance. Undoubtedly, the reversing valve is the most critical component in a heat pump, but the defrost control is close in importance. An evaporator operating in a sub-freezing ambient has the same effect on moisture as an evaporator operating in an air conditioner. The heat removal causes moisture to condense out on the evaporator surface. In an air conditioner evaporator, the moisture is carried out through the condensate drain. In a heat pump, it freezes. The job of the defrost control is to establish the defrost cycles to keep the outdoor coil clear of ice. A heat pump is defrosted by reversing the heat pump cycle, putting it into the cooling mode. The outdoor fan is shut off to allow maximum heat buildup in the outdoor coil. At the same time, auxiliary heat is brought on to supply indoor heat during the defrost cycle. All these operations are controlled through the defrost relay, which is cycled by the defrost control. A heat pump defrost control has two primary jobs. It must initiate a defrost cycle whenever there is enough ice on the outdoor coil to reduce heat pump performance, and it must terminate defrost after the coil is cleared. The methods used for the initiation of a defrost cycle fall into two broad categories. The first type uses a timer which initiates on a predetermined time cycle. The timer initiates defrost every 30 to 90 minutes, as long as the coil is cold enough to support freezing. If the coil is above freezing temperatures, the timer skips the defrost cycle. The second method, control of defrost based on demand, attempts to measure the actual buildup of ice on the coil. Only when the coil is blocked is there a call for defrost. There have been a number of methods tried to sense the buildup of ice on an outdoor coil in a heat pump. They have varied from optical sensors to microelectronics that measure the change in fan load as ice build up on the coil. The two most common types of demand defrost controls today are the air pressure differential control and the two-temperature defrost control. The air differential control measures the pressure differential of the airflow across the outdoor coil. This differential pressure increases as ice builds up on the coil. At a predetermined pressure differential, the switch closes and the heat pump goes into a defrost cycle. Termination of the defrost cycle is most often done with a thermostat mounted to the liquid line. The defrost cycle is terminated when this location reaches the cutoff point of the thermostat, normally about 65 degrees. This method of termination is universally used in all defrost controls. Many defrost controls also have a built-in time override in case the control does not terminate on temperature. Upon termination, the defrost relay coil is de-energized and the heat pump returns to its heating mode. The outdoor portion of a heat pump looks much like a straight cooling unit. The major difference is the addition of the reversing valve, the defrost control and relay, and the metering devices. The indoor unit houses a coil along with the auxiliary heaters and the blower. The indoor coil is specially built to take the higher pressures of the heat pump. Straight cooling coils cannot be used. The auxiliary heat banks are normally sized at 100% of the heating load. In residential heat pumps, the auxiliary heat varies in size from